Okay, time to get going. Let's see here. So first of all, thanks for showing up on the Friday before spring break. Good to have you here. Hope you all have a good spring break, of course, after class is over. Okay, so moving along. Oh, and apologies for my absence. I really was very incapable of coming in for a while long in there. Walking was a real challenge. I'm not over it, by the way. But I can get by, right? But one thing I have noticed is I am just a little cloudy. And I have on a couple of occasions said words kind of maybe a little bit in the wrong order. So if I say something that doesn't quite make sense, please call me on it. Right? Let's set the record straight. I don't want to inadvertently mislead anybody here. Okay. All right. So here's the last thing that y'all saw in the recordings you watched. So it's the big idea is, what if you have a domain that is I'll just put them all in the same big tent, dimensionally awkward. Right? So for example, a curve. Here I have a curve in R2, could have been R3, doesn't matter, but if you have let's say a curve, it's a intrinsically one-dimensional thing, right? It doesn't have any area, right? No area. It's intrinsically one-dimensional. But also it lives in a two-dimensional world, right? So what kind of an integral that we already have would we use for this? And the answer is we didn't have one. So we had to define with a new Riemann sum a new kind of integral, right, called a scalar line integral. This is a real quick review of what y'all have already watched. And then, again, the big idea of how to compute it is to kind of copycat the idea of change of variables, specifically to view the curve as being an image, and then to do a pullback. Right? And the idea of a pullback is I take an integral defined on the domain that I don't like and I rewrite it as an integral on a domain that I do like. Not because of corners or funny looking slices or anything like that, which was our motivation with change of variables, but because of this dimensional awkwardness. And so the parametric curve is this dimensionally awkward thing. It's a one-dimensional thing, but it's in a two-dimensional world. How do I deal? And pulls it back to an interval, which is a one-dimensional thing in a one-dimensional world, and we're thoroughly prepared for how to deal with those kinds of integrals and then details, of course. All right. So I think this is about where we left off. I will point out that there is something a little bit concerning about this formula that we have here. This is our computational formula for how to compute a scalar line integral. And the concerning point is that it seems to involve the parameterization, which of course it kind of has to. That's kind of the whole point here. But wait a minute, parameterizations aren't unique. Right? You can parameterize a curve in lots of different ways. Well, wait a minute. Wouldn't that mean if I took a bunch of different parameterizations and plugged into this formula here, wouldn't I get a bunch of different integrals? Right? And, so now I might have different answers for computing the same thing. And the good news here is that just straight up doesn't happen. This integral that we use to compute scalar line integrals is independent of the parameterization. However you parameterize, doesn't matter. You will always get the same answer. So this is not something we're going to actually show. We're not going to kill time on this point. It is in the book if you're curious. But that's not really what this course is. If this were a more advanced, more sophisticated math major course in the subject, then we probably would, but not in this course. Okay. So anyway, good deal. Parameterize however you like. Okay, so let's see an example. Actually, I'm going to show you several examples. They're all going to be computations done on the same irregular wire. So this wire follows a curve. The curve is parameterized like so. So that defines a curve. You can play the game to think to yourself, what kind of curve is that, by the way? Nice little exercise. Make sure you can think that through. What is that curve? And so, mass is distributed along that curve with mass per unit length. Now keep in mind, the mass is on a one-dimensional thing. One-dimensional things have length. They don't have area. They don't have volume. So here, density means mass per unit length. And that mass per unit length is given by a formula. So it's got more mass per unit length in some places, less in others. And I want to compute the total mass. I also want to compute both coordinates of the center of mass. I also want to compute the moment of inertia around a certain axis, whatever. Okay, so that's a bunch of different questions. Here's the first interesting observation I want to make. All of these different questions, they all pertain to the same wire, right? Which follows the same curve that we understand with the same parameterization, with the same distribution of density, right? So a lot of stuff about these questions is in fact exactly the same. And one of the things that we have to do in particular is take that parameterization and go through and compute the stretching factor that I'm going to need to insert. Well, good news, because all these questions are using the same parameterization, because it's the same curve, because it's the same wire. That means the stretching factor is going to be the same for all of these questions. So you don't have to recompute for every single computation you're doing, and that's a nice little convenience there. Okay. All right, so let's talk through how to compute the mass. My personal, I'm going to call it a point of style, maybe, but I always like to write this down first. Always is an overstatement, but sometimes it occurs to me, and I think it is nice to write this down first. This is just an acknowledgement of the very important point that if you're going to use any kind of an integral, the thing you're computing, it better be an accumulating quantity, right? Because what an integral is the statement that we're going to compute a whole as the sum of parts. And not every quantity of interest in this life has that feature, right? So you got to think that through. And now mass, if I have a lump of Play-Doh, if I break it into two pieces, is the sum of the masses of those parts the same as the mass of the original whole? Well, yeah, of course it is, right? That's the nature of mass. So sure. And then now, of course, mass is mass per unit length times length. Right? That gives us, you'll notice, a scalar line integral. And then furthermore, we know the density that was given in the statement of the question. And we know from previous discussion that y'all watched on the recording, ds is speed times dt. That was kind of one of the big points on the previous page. And we've already computed that speed, aka stretching factor. So a lot of this is just kind of a matter of writing down the obvious. Right? Mass has the feature that's the whole of the sum of the parts, and then just kind of making these little innocent observations all the way down until what you end up with is in fact just a regular old single variable integral here that of course is it's computable. It's a pain, right? This is not a pleasant integral, but this is a doable integral. Okay. All right. Now there's a couple of little things that I left out. How did I know to replace this y right there with t squared? Where did I get that from? Well, keep in mind what this is doing is it's rewriting an output variable in terms of an input variable, right? So y is one of the output variables, and I've rewritten it in terms of that input variable. And that relationship is given by the parameterization. So right here, in the formula for the parameterization itself, that's where I can see that y is t squared. Now let's see, so that is how I know to do that. Is that cool? Everybody happy with that? Okay. All right. Next question. How did I know that the bounds were going to be 0 to 1? Okay, well, because those bounds represent the range of values of the variable for the integral, namely t. And so what's the range of values of t? Well, it says so right here in the parameterization, right? When I parameterize this curve, I had to recognize based on, well, now this is all behind the scenes, right? This was given in the statement of the question. But in general, when you're parameterizing a curve, you write down a formula, sure, but then you got to look at where the curve starts and note what value of t that is. And you got to see where the curve ends and note what value of t that is. And that gives you your bounds. Okay, and everything else, I think, is plug and chug. Okay. All right, very similar thing for the x-coordinate of the center of mass. We have this PAT formula from probably the recordings that y'all watched. I don't remember. Again, a little hazy right now. But y'all have seen at some point some discussion of where this comes from. And now the mass, of course, is something that we just got through computing here. So that's just some number. Right? But the object of interest then is this integral. And it's just a different integral, right? It's mass is mass per unit length times length. Yeah, sure. It's same, of course, same deal. And let's see here. D is speed times dt. Yeah, right. Totally. So a lot of the same development, yada, 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 all the way down. And again, you get to an integral that you can plug and chug. And again, it looks inconvenient. But that's how you'd compute this. How are we doing? Everybody happy? Okay. All right. Okay, a couple more here. And these are for students to read. So the ideas that go into these other two examples are the same kind of thing. Very readable, I think. You'll notice how the calculations copycat, right, so much. Like, again, that same mass is mass per unit length times length, etc. A lot of it's really the same. Just starting with different integrals. For example, here's how you compute moment of inertia, etc. Okay, so make sure to read and follow through and think through all those details. Okay. Office hours if you have any questions, of course. Okay, another example. Now this one's just a little bit different, just to mix it up. Here, we've got a fence. This is a weird fence. The fence sits on top of the unit circle. So I've got the unit circle, and this is a little section of the unit circle right there that we're, blowing up for visual convenience. And the fence, though, goes all the way around the unit circle. And this is a weird fence in that the height is not constant. So in different places, that fence is taller, and in other different places, the fence is shorter. Now, why would that be? Maybe this is a garden of some sort, and I like the fence to be shorter on one side so I can see it better because it's pretty, and it needs to be taller on the other side because of the sun comes in at some angle, and I need to give shade to certain plants that don't grow. Whatever, something along those lines, right? Maybe it's just for the artistic appearance of it all. This would be kind of a wild-looking fence. Okay. Anyway, how are we going to compute the area of this fence? Maybe I need to stain the fence, for example. Need to know how much paint to buy. You buy paint by area. Okay, so the first observation I'm going to make is that area is an accumulating quantity. The total area is the sum of the areas of the pickets in the fence. That makes sense to everybody? Whole's the sum of the parts. It really is. right? So I'm not just claiming it because that's what we do here, right? That's how a fence works, right? So again, natural, reasonable point that we have to think through, but that does in fact work out. Okay. Now next, I'm going to point out that this area of this picket, what I'm calling DA here, I can compute that pretty explicitly as height at that location, which of course I'm given, times, let's see here, color choices. I'll use green here. Times the width of that little, what I'm calling picket, which of course is a little piece of my curve, and a little piece of the curve we call ds. Right? That's the length of that little piece of curve, ds. Okay, so knowing that area, of course, is height times width, like so. That's how we motivate that we're interested in this scalar line integral. Does everybody see where that scalar line integral came from? Notice I didn't pull it out of a previous page of the notes, and it wasn't given to us explicitly. We had to motivate. We had to go through kind of some geometry arguments. I had to think about what a scalar line integral is as a Riemann sum, right? To conclude that this scalar line integral is what we're interested in. And that's an important part of the problem, right? Being able to look at a question and realize, hey, what am I computing, and how do I break it up into pieces, and putting those pieces together, etc., and coming up with the scalar line integral in the first place. Okay. Alrighty. So, to compute that scalar line integral, I know that the move is to parameterize my curve being the unit circle. Conveniently, we have an existing parameterization for the unit circle. Now, you won't always have, of course, an existing memorized, pre-memorized parameterization for your curve, but we spent a bunch of time back in chapter 1, right, really early in the course, talking about how to parameterize things and different methods for how to parameterize things. So this is where all that stuff's really going to kick in, right? This is where all that stuff becomes really useful and important. So anyway, that said, there's the parameterization for that curve. And we know how to take velocity. And we know how to take the magnitude to get the speed. And that gives us our stretching factor. So our stretching factor in this case is 1. Okay. All right, now let's see. Next thing, I've got to figure out what to do with my height formula. And just a reminder, the height formula was given. It was explicitly given. The height formula is given in terms of x. And again, I got to think to myself, wait a minute, how do I get rid of, that's an output variable, but my integral I'm trying to develop here needs to be in terms of t, the input variable. And how do you relate outputs to inputs? Well, the parameterization. And again, you can see it right here. The parameterization explicitly tells me, for example, that x is cosine t. And so that x right there, cosine t. All good? Everybody's happy? Okay. All right. Okay, so moving along. So this next example is it's going to work out a little bit differently. I want to remind you, actually, let me not get too ahead of myself. I want to remind you of this old formula right here. Let me do it like this. This formula right here that tells me we can compute work as force dot displacement. This was an improvement over an old high school formula that we saw, that work was scalar force times scalar distance asterisk. Oh, hey, by the way, this only works if the force is in the direction of the displacement, and if it doesn't, then you got to think about the component and the blah, this whole discussion, right? A huge, enormous asterisk, all of which goes away just by recognizing what was the truth in the first place, which is that we shouldn't think of forces as being scalars. They're not. They're vectors. And we shouldn't think of displacement as being scalars. They're not. Whenever you move, whatever distance you move in a direction. It therefore is a vector. So dot product just makes that all that asterisk business go away. But it does remain, unfortunately, that this assumes that displacement is over a straight path. And it assumes that this force vector is constant. Always the same. Let's pretend these are always the same vector. It assumes a constant force. Right? So that is just simply not always our picture. So we want to recognize the perfectly legitimate possibility that the force might not be a constant. Let's look at this vector field down here. Right there, vector force, not a constant. It varies widely. Right? And then likewise, what if my displacement doesn't happen over a straight line path? Again, for example, like so. Let's maybe that's that path. How would I compute the amount of work here if I'm walking along a curved path and if the force changes as I walk? So, for example, now maybe this is a curved path on a hillside and I'm out for a hike, right? And maybe these arrows represent the force that I have to exert to prevent myself from tumbling down the hill, right? Namely, I'm on the side of the hill and it's steep, and therefore gravity pulls me somewhat, downhill, and that will have a direction. So, of course, the hill is not uniform, and uphill is a different direction depending on where you are. Right? And so you could totally have a non-constant force, and of course trails are, pretty typically not straight lines. How we doing? Is everybody on board so far? All right. Before we go along, I will point out that there is a little bit of a eyebrow-raising concern here already. And that is, if I want to know how much work it takes me to hike this trail, it really matters whether I'm going up the trail or down the trail. Right? The direction that I go makes a difference. A lot easier to go down than it is to go up, right? Anyway, notice that didn't come up when we were painting the fence. Right? I could have parameterized this curve the opposite direction. Would I get a different amount of paint if I painted clockwise instead of counterclockwise? Nonsense. Obvious nonsense. Right? Likewise, when I'm looking at the mass, let's say, on this bent wire question that we were talking about, will I compute more or less mass or possibly negative mass if I count from, one side as opposed to the other side? Silly, right? Of course not. It's preposterous. So already, I'm a little concerned that something's different. Something's changed here. We're going to have to figure out how to account for this. Right? How do we deal with the fact that I've got to recognize which direction this curve is going? And so to start off with, I'm just going to come out and say it. We're going to just have to recognize that this thing, what we're going to call an oriented curve, and the word oriented is a reference to what we call orientation. The orientation meaning an understanding of which direction is the direction that we are moving along that surface. It's called an orientation. I said surface. Again, that's the fever probably. Curve. Which direction am I going along this curve? Everybody happy? All right. So that's going to come up in a bit. Okay, that said, look, I can totally, just like several other problems that we've done previously, I can totally chop this curve up into pieces. I can totally compute the total amount of work as the sum of the incremental amounts of work. Right? I mean, look, if you burn, 10 calories on that little piece of curve, and then you burn another 15 calories on the next piece of curve, et cetera, et cetera. You just add up those numbers, right? So it's clearly an accumulating quantity. And so the whole is the sum of the parts. And then on each little piece, notice on that piece, it's approximately straight. And furthermore, notice on that piece, while the force isn't exactly constant, it's pretty close to constant. Because that little curve, keyword is little. We don't move very much on that little piece of curve. So if you don't move very far, then